Beginning the presentation, the title of the research is Systematic Approach of Topical Herbal Anti-Inflammatory Drug Development to In Vitro Formulation Studies. Introduction. Herbal analgesic and plant-based remedies used for in centuries in traditional medical systems like Ayurveda, traditional Chinese medicine, and Unani. These herbal remedies have been used to alleviate conditions ranging from headache and muscle ache to more complex pain syndromes such as arthritis, neuropathy, and inflammation. Microemulsions are thermodynamically stable, isotropically clear, dispersion after emission liquids such as oil and water, stabilized by interfacial famous surfactant and molecule with a size range of 5 to 200 nanometer and have a very low interfacial tension. Microemulsions can be classified as oil in water microemulsion, water in oil microemulsions. Microemulsions are widely used in oral route, nasal route, tropical route, and ocular route of drug delivery systems. The objective of the research to study the pharmacognostic characteristics of the crude drug, to establish its identity and quality, and to identify major phytochemical constituents, to employ TLC and HPLC technique to standardize and quantify the plant extract using biomarker, along with studying in silico parameters using computational tools. To formulate and optimize a microemulsion using quality by design approach and to develop a topical formulation utilizing the optimized microemulsion for enhanced herbal extract delivery to perform comprehensive characterization of microemulsion to the topical formulation, including physicochemical properties and in vitro studies. Rationale. Microemulsions are ideal for topical therapy system due to their thermodynamic stability, optical clarity, easy preparation, and high absorption rates. Glutamate, that is Thymus brachyfolia, known for its analgesic, also antinociceptive, neuroprotective, immunomodulatory, and antioxidant properties. Despite its therapeutic potential, research on incorporating glutamate in drug delivery system remains limited, highlighting the need for further investigation. Moving with the methods and results, the plant extract was categorized for various phytochemicals consisting of alkaloids, tannins, and phenolics, flavonoids, glycosides, terpenes, and steroids and saponins using established procedures. It showed that the Puluche extract showed positive results for alkaloids, tannins, and phenolics, flavonoids, glycosides, terpenes, and steroids. The crude drug was also standardized using established procedures according to Indian pharmacopoeia. The parameters selected were moisture content, total ash value, acid insoluble ash value, water soluble extract, ethanol soluble extract. The values were compared with IP limits. It was seen that the values were within the range of the given IP limits. The extract was standardized using TLC and HPLC technique. The mobile phase used was N-butanol ethyl acetic phosphoric acid in water with biomarker as a berberine. The plant extract has well as the standard biomarker berberine showed a RF value of 0.76, confirming its presence in the Guduchi extract. The molecular docking was done by using ligand has berberine and standard diclofenac sodium. It was seen that berberine showed highest binding affinity with COX-2 enzyme and protein 4D-JH, that is human kappa opioid receptor. These are the images with the binding affinity of COX with the protein COX-2 and human kappa opioid receptor with diclofenac sodium as well as berberine. The berberine was also evaluated for toxicity studies and ADMA studies of berberine. The berberine followed all the 5 rules of Lipinski. Berberine also showed the toxicity of class 3. There was inactive organ toxicity, here, neurotoxicity, nephrotoxicity, cardiotoxicity was seen to be inactive. Moving with the pre-formulation part for preparing the microemulsion, screening of oil sulfate and co-sulfate does to determine the optimal solvents for solubilizing decodified extract, evaluation of its solubility in various oil, surfactant, and co-surfactant was done. A standardized procedure was followed by 200 mg of the extract was added to 1 ml of vehicle. The mixture is sealed, sonicated for 10 minutes and then subjected to 24 hours of shaking on an orbital shaker at 37 degrees to ensure thorough mixing and solubilization of extract. After shaking process, each sample was centrifuged at 3000 rpm for 15 minutes. Subsequently, 0.5 ml of the filter supernatrins were diluted with methanol. From the selected surfactant, Twin 80 was selected as a surfactant, Acrin MC8 was selected as a co-surfactant, and eugenol oil was used as an oil phase. The spectrophotometric determination of Guduji extract was done in methanol as well as in phosphate buffer 6.8. The calibration curve was plotted by using solvent as methanol with the R-square value of 0.993 and that with extract in phosphate buffer 6.8 with R-square value of 0.988. Total phenolic compound content. The presence of significant amount of polyphenols indicates stronger antioxidant activity potential of cordifolia extract, which is important as phenolics can reduce oxidative stress and prevent damage to cell and tissues. Oxidative stress is often linked to inflammation and pain, and by reducing oxidative stress, phenolic compound may help to elevate pain. It was seen that Tenosula cordifolia extract consists of 71.28 plus minus 1.21 mg gallic acid equivalent per gram of total phenolic content. For facilitating the ratios of S mix, that is surfactant, co-surfactant, water, and oil, pseudo-ternary phase diagram was plotted using phase titration method of microemulsion. The different ratios of 1 is to 1 of S mix 1 is to 2, S mix 2 is to 1, and S mix 3 is to 1, among which S mix 2 is to 1 showed highest microemulsion region. The microemulsion region was further optimized using quality by design approach. For the QPD-based optimization, I-optimal design was used. The design model was special cubic. There were 17 runs. According to table 3, the design constraint were A has S mix, B has oil, C has water, and the combination of A plus B plus C is equal to 1. The lower limits and higher limits were decided. Based on the quality by design approach, the 17 runs provided. The evaluations were done as response 1 particle size in nanometer, response 2 zeta potential MV. Figure 18 and Figure 19 explain the model graph and 3D surface graphs of particle size, the model graph and 3D surface graph of zeta potential. The yellow region in the first figure shows the design space. It was seen that increasing the concentration of S mix, water, and oil at the same time increases the particle size. Whereas compared to in combination of AB, BC, and AC reduces the particle size. The yellow region is the design space for zeta potential. The red region shows the optimized region of the zeta potential. It was seen that increasing S mix, oil, and water together increases the zeta potential, whereas AB, BC, and AC in combination gives the optimized zeta potential. Based on this result, evaluation of extrapolated microemulsions were done. The evaluation was done for both placebo microemulsion and extracted microemulsion. The particle size for placebo microemulsions were 47.94, that were extracted microemulsions of 40.14 nanometer. The zeta potential was found to be minus 26.4 millivolt, and that of extracted microemulsion was minus 38.08 millivolt, explaining the stability of the microemulsions. Percentage transmittance is an important parameter in evaluation microemulsion. Percentage transmittance measures the transparency of the microemulsion. The placebo microemulsion showed 99.38%, that of extracted microemulsion showed 97.76%. The centrifugation studies show that there are no phase separation seen in microemulsion. The rheological studies were done determining the viscosity and surface tension of the microemulsion. The viscosity of the placebo microemulsions were 34.00 plus minus 0.24 CPS. That of extracted microemulsion were 36.00 plus minus 0.24 CPS. The surface tension measures in times per centimeter. The placebo microemulsion showed a surface tension of 28.77 plus minus 0.2. That of extracted microemulsion showed 28.65 plus minus 0.2 of surface tension. The transmission electron microscopy of the microemulsions were done. It was seen that the global side were measured from 20 to 50 nanometer. The optimized microemulsions were further incorporated in the carbopool-based shell. The appearance and texture of the microemulsion were green, transparent, and smooth. Also, the microemulsions were compared with the normal extract-loaded shell. It was greenish, transparent, and smooth. The pH were between 5.9 to 6.24. The spreadability was 6.8. That for extract-loaded shell was 6.75. The viscosity was 108.30 plus minus 24.74. That of extract loaded gel was 115.87 plus minus 20.96. The drug content which was determined by UV was 98% of microemulsion gel, and that of extract loaded gel was 99%. The drug content was also evaluated in HPTLC technique, for which microemulsion gel, and that of biomarker was compared. It was seen that the RF values of the three were all same. promising the presence of biomarker in that of microemulsion and also in the microemulsion. The in vitro permeation studies were studied using nylon 6 membrane and phosphate buffer 6.8. The in vitro permeation studies were done for microemulsion, extract loaded gel, and standard diclofenac emulsion. The percentage cumulative release of diclofenac emulsion was 92.23%. That of Tinospora cordifolia extract loaded gel was 80%, and that of Tinospora cordifolia extract loaded microemulsion was 87.05%. The steady state flux was also calculated, and permeability coefficient was also calculated in units of centimeter per hour. The PCV-DISO of the formulation was studied. The diclofenac emulsion showed PEPA's model. The Tinospora cordifolia extract loaded gel also showed PEPA's model. That of Tinospora cordifolia extract loaded microemulsion gel also showed PEPA's model. The in vitro antioxidant study. High antioxidant activity implies better scavenging of this radical, which can reduce cellular damage and inflammation, a common source of pain. Ascorbic acid exhibited 94.47% inhibition, while the formulation showed 90.69% inhibition, and the plant extract demonstrated 89.39% inhibition at the concentration of 500 microgram per ml. The IC50 value for standard ascorbic acid was 14.83 microgram per ml. For Tinospora cordifolia extract, it was 69.83 microgram per ml, and that of formulation, it was 57.64 microgram per ml. The formulation was also evaluated for in vitro anti-inflammatory studies by two methods. The first method is by protein denaturation method. Denaturation of tissue is one of the well-documented causes of inflammatory and arthritic disease. Production of autoantigen in certain arthritic diseases may be due to denaturation of protein in vivo. Agents that can prevent denaturation therefore could be worthwhile for anti-arthritic and anti-inflammatory drug development. The sample plant extract showed 70.66%, sample microemulsion showed 71.29%, sample microemulsion showed 71.58%, showed moderate activity as compared with standard diclofenac sodium 82.94%. The other method was protein inhibitory action. Neutrophils are known to be rich source of serine proteinase and are localized at lysosomes. It was previously reported that leukocyte proteins plays an important role in the development of tissue damage during inflammatory reaction, and significant level of protection was provided by proteinase inhibitors. Plant extract microemulsions and gel showed a moderate activity as compared to the standard drug diclofenac sodium. The brain trim lethality assay was done to calculate the toxicity of the microemulsion. The brain stream lethality assay is a quick, cost-effective, and reliable method for evaluating toxicity of natural synthetic compounds. The BSL assay was carried out by using brain stream. The given sample showed less mortality, so the sample plant is non-toxic to the brain stream. Moving to the summary, conclusion, and future prospect. In conclusion, pain represents a multifaceted experience shaped by both sensory perception and emotional response, often linked to actual or potential tissue damage, and subjectively interpreted to personal lenses of knowledge and experience. A successful attempt was made to develop, identify, and study the pharmacognostic properties of the powder to establish procedures. A qualitative and quantitative phytochemical screening confirmed that the extra cordifolia extract of Tinospora cordifolia is enriched with phytoactives, including alkaloids, polyphenol, flavonoids, and terpenes. The study successfully formulated a microemulsion using pseudogenetic phase diagram, achieving a particle size and theta potential with specific ranges essential for ensuring the homogeneity and stability of the emulsion. In silico screening via computational tools of performed, it helps to predict the analgesic potential of berberine. The DPP scavenger antioxidant assay demonstrated significant antioxidant activity. These are the references. Thank you.